we're going to review a little bit of the unit circle, and from there we're going to go to waveforms and try to add them together. So the unit circle, if you remember, is a circle where the radius is always 1. And if you can picture like a dial, the arm of a clock, moving around, circulating in this circle, the length of this dial is always 1. And as it is moving, it has an angle here, and the angle changes. Then, of course, if you're looking at the projection of this dial along, for instance, this axis, we can call this projection A. And the length of this projection, that will change as the dial is moving. And similar on this axis, we also have a projection. We can call it B. And this projection will also be higher and lower. 1 always as the maximum, but sometimes 0, or minus 1. But the length of the dial never changes. That's always 1. So let's look at a little bit how this differs. So let's start with a viewing position. So not looking at it from the front like we're doing here on the board, but we're changing our position to actually look at the projection on the vertical plane here. And then as a starting point, the dial is over here with a phase of 0. And we don't see any length at all. But as the dial is starting to move in this direction, it is growing. And up here, it becomes +1, then waning again, becoming -1. And what we have here is a sinus curve. And indeed, this projection in relation to the length of the hypotenuse, which is 1, is sinus 4 theta. So we can change the viewpoint. We can maybe look from down, under here, looking at the projection on the horizontal axis instead. Now, when we start, the dial is fully visible, so we can see it as a length of 1. But then when it starts to move and the theta is increasing, it is starting to be lower in amplitude, and then minus, and growing again. So if I had drawn completely perfectly, what we would see here is a sinus curve and a cos curve. Because the relationship between A and the hypotenuse is cos for the angle. So as you can see, the sine and the cosine, they have exactly the same shape, at least when someone is drawing them properly. But the only thing that differs is the angle or the phase shift between them. The phase between the peaks here has as a fixed one. So the phase relationship between the two is actually 90 degrees, or pi half. And what if we had 2 dials like this moving around? 2 waves moving together. What happens to them when they interact, when we have them together? Well, actually, they add up. All waveforms, they superposition in this way. And we can do it in several ways. If we want to see the resulting waveform, we can do that in several ways. We can add the vectors together, and that's quite simple. We take one of the vectors and translate it along so that it comes tip to tail, like that. And the resulting vector is actually, and it should be perfectly along this axis actually. The resulting vector has a length that is longer than 1 because they're all contributing in that sense. But the position of the vector is slightly changed. So what if we do the same thing here? Now we have 0 here and 1 here. That added together leaves us with a 1. Here we have both positive waveforms, and they have equal values. So we just add them on top of each other, and the resulting maximum amplitude comes up here. At this point, the cosine has a 0, but the sinus is not. So here we have a value there, adding them together. Similarly, down here, the sinus has a 0 value. The cosine is over here at a minus value. Here they're both minus, and the resulting amplitude becomes minus more than 1. So if we add these two together, yeah, we should get something like that. So a waveform that has a slightly different shape to it, but still sort of sinusoidal approaching. And the frequency of this one is the same. They're both moving with the same frequency. They're both rotating with a fixed angle. So the resulting waveform is sort of approximating